to learn about conformations of alkanes. Alkanes can form different conformers or rotamers, and those are just 3D arrangements that come about from rotation about the single bond. So, from rotating them about a carbon-carbon bond. So, with these single carbon-carbon bonds, they're free to rotate. The staggered conformation is going to be preferred. And in the staggered conformation, what we see two hydrogens here and here with one in between in three-dimensional space. This one's in between. And so when we stare down the central CC bond, where we see one carbon right behind the other, we see that this hydrogen in front is in between these two hydrogens that are in the back. Now, let's actually use some different colors. Let's do hydrogen in the front, hydrogens in the front so that we can see those a little bit clearer. Let's do, these three can be our hydrogens that are in the back. And so they're staggered in between the other hydrogens. And right at this point in the center, we're staring down the carbon-carbon bond. So this is one carbon with another carbon atom directly behind it. Now, if we imagine spinning or rotating, really, to me, it looks like this back carbon atom so that these hydrogens move over 60 degrees, then what we see is eclipsing. We see these hydrogens directly lined up. So my back hydrogens are totally lined up with my front hydrogens. Here's my three rather that are in the front. And so they're lined up or eclipsed. And this is not favored because there's a lot of overlapping of electron clouds here. What's on the outside of the atom? Well, they're electrons. And so the negative electrons of one atom get too close to the negative electrons of another. That electron cloud overlapping causes that eclipsed conformation to be much less favored, and the staggered conformations to be the favored conformation. This is why we see all of these zigzag structures drawn for straight chain alkanes, because they really prefer being zigzag, because being zigzagged naturally makes the molecules completely staggered. Torsional strain is used to explain why these alkanes want to be staggered. As you move from staggered to eclipsed, there's added energy, 3 kilocalories per mole, and that added energy or increase in energy is due to torsional strain, due to the fact that these electron clouds are going to have more overlapping when they're eclipsed. And they're going to repel, and so therefore the eclipsed is going to be a higher energy structure. If you put larger groups on the molecule, that makes the strain even worse. Let's say that this were a CH3 and it has another CH3 behind it. Well, that would be due to a 1, 2, 3, 4 carbon chain. Let's say it's butane. You're going to have even more overlap of electron clouds here, and there's an additional name for that. That name is steric strain. So putting larger and larger groups in that eclipse conformation adds steric strain on top of torsional strain and makes that eclipse conformation even less favorable for something like butane. You'd have to add in even more energy to go from staggered to eclipsed in the case of butane.